Alright, welcome to a new day. Let's talk about strings and floating point numbers. Two completely different topics, but why not? We're going to put them together in this set of slides. So let's assign a little bit of reading just to make sure we know floating point numbers. So there's some floating point sections of chapter 4, which I may have already assigned, actually, I can't remember. But go through those if you haven't already, because we're going to be talking about them. Alright? So yeah, let's get straight on into strings now. We're going to focus on messing with strings, C strings specifically, in assembly. All right, so you got a bunch of fun header files here that have cool functions that maybe you've used before. So standardIO.h has, here I am, standardIO.h has, among other things, that's where printf lives, it has getchar and putchar, and they do kind of what you would expect. So getchar gets a single character, gives it back to you as an int for some reason. Well, it's going in a W register anyway, I guess. Gives you back an int, but pretend it's just a char. All right, it really is just a char from the standard input, and then putchar prints a single char to the standard output, and for some reason, again, it takes an int. All right, so just pretend it meant char. All right, that's all I mean by that. So getchar is like the C equivalent of, that is way too big. Let me fix that. Getchar is like your C equivalent of the C++ like cin.get, if you used that before. Like it's a single character from the user, from their keyboard. All right, and putchar is just the equivalent of outputting a single character. It's like cout, give it a single character C. Okay, so there's that, and then you have other nice library files like ctype.h is your CC type from C++, which I force my 40 students to use a lot. You've got all these functions that like test and see if like was a character a digit, an alphabetic character, convert a character to lowercase to uppercase, stuff like that. All right, so that's useful stuff. And all of those is blank functions, is alpha, is digit. They return not a bool, all right, because this is C. The bool type doesn't actually exist in the C language, so it's going to return an int. Okay, like is digit. It takes a char, think of this as a char, it returns an int though. And that int is 0 if it means it was false, like it wasn't a digit or whatever, and it returns anything other than 0 for true. So you have to compare against 0, or you're going to run into trouble. Don't assume that 1 means true. It will not mean true. Okay? So that is just something to watch out for there. And then string.h, C string from C++, dun, 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 holds many things, many fun things, one of which is strlen. Okay, that's going to give you the size of a C string, not counting that null terminator character though. I'll just give you the number of real characters in the string, and there's some other very cool ones that you can look into. All right, so let me just give you a couple fun examples of string processing, and we'll go from there. So the first example, let's make a program in assembly that counts the number of stars that the users type. Maybe they're typing a bunch of characters, including stars, but we want to count just the stars that we see until the end of file is given to us. All right, end of file. And that is a special character, in fact. If you give a file to the standard input, it will, once it's finished being sent there, it will send the special character to mean that it's done. It's called the end of file character, and Control D is a way to send it if you're typing it yourself on the terminal. That's also why Control D logs you out. It's like, I am done with my terminal session. End of file. Okay, as if what you're typing to the terminal is just one big file or something. So there's that, and this is actually why getchar needs to return an int, among other things. It will return -1, a full 32-bit -1 for end of file, so in a W register. So we'll be looking into that, but that's like a special character. It's not actually part of ASCII. It's just a special character that's not a character in a sense. All right, so let's do that example. All right, so end of file. Let me just write this first. End of file. It's like it's the equivalent of the null terminator for files. It's the \0 equivalent for files. And that is, I think, what I want to say about that. All right, so let's make this program. Here I am on the server, ready to go. I'll do a countstars.s file, I guess, and I would prefer to just steal the main function from some other file we've already written. So let's look at lecture 10's, I got a convert.s, is there a main function there? course there isn't. Let's try again. What else we got? Some array? Is that a... Again, no main function. Tough luck for me today. Let's try lecture 8. I guess it would have been faster at this point to like test for it. What do we got? What do we got? Sum 10. Test sum 10. That surely has a main function. Yeah, there we go. Okay, cool. So that's what I wanted. Just let me get out of all this. Let's make this file have what I want it to have now. And it'll return 0. And do we want this data section? I'm not sure yet. Sure. Let's keep the data section, but we can change things later. So cool. I have a main function ready to call other functions because I'm saving LR on the stack. Awesome. And my goal is to get a bunch of characters from the user and see how many stars there were. So let's just keep calling it in a loop get char, because I'll just get a single character. Let's do that multiple times until we see the end of the file character. That'll be -1, and then we'll stop and print how many stars we saw. All right. So I need to save how many stars I've seen, and I'm going to be calling functions in between. Get char is a function, right? It can clobber any scratch register of mine. So I better save my count in a register that, like as an int, for example, in a W register, but in a place that's saved, in a saved register. So W19 is a good one. Start my count at 0. That'll be the number of stars I've seen. And because I'm messing with a saved register, I have to save its old value. So I better store X19, the whole thing, somewhere in SP. There. And I better restore it later. Down here. Alright, so load into X19, and then clean up the stack. Cool. So now I have this place that will be safe across function calls, and now I want to repeatedly call get char, which takes no parameters, no arguments, until we see end of file. Alright, so this will be my loop. So I just want to call get char, just like that in C, and just like see what I get back. And it takes no argument, so I can just immediately BL get char. Alright, so there it goes. And now its answer, it's given back to me a character, and that character is going in W0 as an int, because it might have been that -1 value EOF. Okay, so W0 right now holds the character the user typed, and we want to stop counting the stars, right? See if this was EOF or not. Stop counting if it was EOF, which is going to be -1 on our system. All right, so let's compare the value in W0 for -1 against that, and if it's equal, BQ, we will be done, and we'll put done down here. We're not ready to like quit the program. We still need to like print out how many stars we saw, but that will stop us. And now, all right, we knew we didn't have a EOF, but we're not sure did we see a star character or did we not? All right, so let's check for that. So now let's see if W0 was a star character. So we'll compare W0 for, you can do it just like this, whatever the star character's ASCII code was, and if it was, we'll count it. Otherwise, if it wasn't equal to, because I like to do my inverse comparisons, we'll make like a label called like not a star. All right, but if it was a star, we're going to fall through, right? And we should add 1. If it was a star, add 1 to W19. So add W19 number 1. There we go. And if it wasn't a star, let's have not a star right here, right? It's like it didn't add anything, but definitely what we need to do after all this is one iteration of the loop. We want to go back up to the top and get another character because we're not done yet. We have not seen EOF yet. So continue looping. So I will BAL to the loop. Okay? And so that'll be the loop, I think. It's a good looking one. And once we're done, we have a value in W19 now that is our count of how many star characters we've seen. And so we'd like to print out with a call to printf, eventually, how many characters we've seen. And so let's give a format string that'll take the number of stars and print it out in a pretty way. Call it format cstring ASCII's number of stars %d new line. All right, so let's put that in. The format string needs to go into x0, and then into x1 goes the actual number of things that will be what the %d is looking for, that second argument, and that's the current value that I have in W19. Move that into, sorry, not x1, but w1, because it's just an int. All right, so that should do it. And let's see how well we did. Count stars, -o count stars. Oops, I called it a file name with a dot, of course. Let's fix that. There we go. Compiled. Can we run it? And so I can just start typing now, characters, and eventually I can put stars, so there's 4 stars total, hit enter, and eventually once you type Control-D, it's like, all right, I'm done getting characters. And it saw exactly 4 stars, and yes, it's right. It found them, okay? So if you type Control-D, you will actually get some stars, but there's a way to give a file itself to a program, okay? Maybe you've seen this before. It's like if you run your program, and you say, on the terminal, if you say > symbol, and you give a text file, it will pretend to type that text file as into the standard input of your program. So this will type the entire file and give it to the program, and also once the file is complete, it's typed it all in, it'll send the EOF character for you. So let's make some text files. So I'll make a, I don't know, I'll make a file1.txt, which just have a bunch of stars, wherever. So there's a few stars. File2.txt now. Let's just have that be. Let's have it have no stars. That's a good edge case to test. So there's a second file that has no stars at all. So if I run my first program, if I run my count stars program on the first file, say file1.txt, apparently there's 21 stars in this file. And if I run it on file 2, which was just hello world, then it's like, yeah, 0, which is correct. So that's good. Looks like it figured it out, right? And yeah, that's how you give files to a program, and it's like typing it for you. And it'll send EOF for you as well, okay? That's my first example. And for my next one, let's do a program that takes as input, just with getchar again probably, and we'll just lowercase all of it. So we'll take whatever we saw with getchar, and we'll lowercase it, and we'll spit it back out probably with putchar. That seems like a good idea. Again, we're going to have to use EOF, check for EOF to know when we want to stop reading characters. But I think that is a good one. So let's lowercase whatever is given to us. So I will absolutely be stealing this file, lowercase.s. Let's see. Keep all this here. Don't even need printf anymore. I don't honestly think I need an x19. Should I get rid of that? Yeah, I don't think I'm gonna need a scratch register. Or a saved register. Everything can be done in scratch registers. Because what I want to do is, or sorry, I should have saved the loop that keeps looking for characters. I don't think I need x19 or w19 though. But the loop that keeps looking for characters, that is nice to have, okay? Get rid of those, get rid of the restoring x19, unnecessary. But this getchar loop, we are happy about that. So, and the BEQ done as well. We like that. So this is going to keep on running the body as long as we don't see EOF. And so we've got a character in W0 now. What do we want to do with it now? It's lowercase it, lowercase whatever character we just saw, since it was an EOF and we're not done yet. Lowercase it by calling toLower on it. Right, so toLower is going to take a string, or take a character, give you back the lowercase version of that character. So I want to call toLower on whatever character I just got, and it's already in W0. That's perfect. So if I can just BL it, right? Lowercase, the character we got, it's in W0. That's where it needs to be for the argument to toLower. We are set. And just say BL toLower. And then I'd like to print out the character that's been lowercase potentially. Again, it's in W0 again, which is both the return spot for the previous function as well as the argument spot for the next function, isn't it? So print out that lowercase character. And so I can just BL putchar, because again, the character that I got back from two lower is in W0, and that's where it needs to be for the one argument of put char. That's beautiful. Isn't that nice? And that's an even shorter program, isn't it? So there's that. I don't actually need anything in the data section, but it can stay there for posterity, just for fun. Lowercase, and I don't know, we can start typing our own stuff, like hello world 1 2 3, and it'll just spit out the lowercase versions. It gets a line at a time. That's kind of how the how get char works in Linux. Hi 1 2 3 4. I don't know. Once you type Control D, it's done though. And you can also, of course, send a file. So like file2.txt was hello world with a capital H, and it definitely made that a lowercase h now. Okay, so yeah, those are my two examples for strings for the day. I want to draw for you now an example that you will be implementing in your lab, in a future lab. So I'll just give you the idea, and it'll be your job to complete the task. All right, so this is a finite state machine. All right, if you've never taken CSCI 26, it's possible that you haven't seen one of these yet, but it's just an idea of like the concept for a state machine is like you're in a state. You're in one state or another. You start out in this particular state, but you can move around into different states, and you can stay in your states. And by moving around within your state machine, that can cause things to happen. All right, that's the best way that I can explain a state machine to someone who hasn't heard of one yet. But hopefully, as I explain this particular state machine, it will help. All right, so here's the idea. You can make and use this finite state machine to count words. All right, count the words in a string or just the text that the user gave you with get char or whatever. But here's the idea. Here's how you can count and always get accurate the number of words, separate words that a user gives to you. And this is a non-trivial problem. If you haven't tried it before, it's definitely a little funky, because like you might think, oh, how about I just count the spaces that I see and like add one, because spaces separate words. Well, that all breaks down if the user wants to put extra spaces all over the place, including like tabs and new lines. So like pretend that this was the text that the user gave you with extra spaces and some tabs and new lines as well. Underscore means space here, of course. You can't just like count the number of spaces and add one anymore. Now it's incorrect. Okay, so we need to get fancier, and here's how you do it. All right, so there's two states to our state machine, and you can either be inside of a word or outside of a word. And when you start your life, you're gonna essentially send each character of your string that you want to count the words in as input to your state machine. That's gonna drive it. All right, so you start out having not looked at any characters yet. You're not inside any words. So the very first state you're in is the outside of a word state. Okay, and then the idea is, as you see characters, you'll send this character in. That will bring you to a different state. All right, so like when you see the T character, you were in the outside of a word state, but you've now seen like a character that's inside of a word, haven't you? And the T starts a brand new word. So if you see a non-space character, that will transition you, that's the technical term, transition you to the inside of a word state. Okay, now we've seen a new word here. And all right, you see the H character. You're still inside of the same word. You're not outside of a word anymore. You're still inside of a word if you see any more non-space characters. Okay, and you're using each character to drive this state machine. The E, again, still inside of a word. It's a non-space character. But the second you see a space, now that word's over, right? You're in the no man's land between words now, and so you should transition on a space character, any kind of space character, tabs and new lines included, to the outside of a word state. Okay, and then as long as you keep seeing space characters and you're in that outside of a word state, you should stay outside of a word, because you haven't seen another word yet, have you? Space character. And yeah, the second you see like another space, the second you see a Q, you're outside of a word. Now you're inside of a word again. That's actually how you notice new words. This transition right here is how you notice new words, isn't it? Okay. And so, if you kept track of a count, and every time you followed this transition, if you added one every time you went here, because this is the transition that notices a new word, isn't it? So if you always add 1 right there, like, and you started at 0, of course, you saw the T, you added 1, and then we just went back, right? We just saw the Q for quick, boop. Now we'll add 1, and the UICK keeps us inside of a word, right? The space brings us back out, so now we're outside of a word again. We're in the outside of a word state. You see the B, that's the third character. Does that make sense? Or sorry, that's the third word. That's the new start of a brand new word character, okay? And you see the ROWN, you stay inside of a word, and the spaces transition you to outside. You stay outside, but you see that F, that's a brand new word, so you're going to take the transition. You're inside of a word now. You don't know how long it's going to be, but that was the start of it. You see the O, the X, you stay there, okay? And then the 3 spaces transition you and keep you in the outside of a word state, but that's not really doing anything good for you. There's no new progress after that. There's no new words, okay? So do you see how that's correctly counting the number of words if you just were to implement the state machine, all right? And add 1 to account every time you followed this transition? And so now the age-old question is, how do you implement this, okay? You're just going to have to keep track. You're going to read a character at a time from your string, and you're going to have to keep track of which state you're in. Your starting state was outside a word. You could have possibly transitioned to inside of a word, though, so you have to keep track of where your current state is. You'll need a variable for that, or a register in your case. So just make a state variable somehow in your code, using a register maybe, and just like encode that 0 means I'm in the outside of a word state, and like 1 means I'm inside of a word, and every time it changes, you like change it back, okay? That's how that works. You see a space character, you're in the outside of a word state, well, just keep changing it to 0, because that means you're still outside of a word, all right? So it's just essentially a big long if statement. It's like a bunch of nested if else's that like keep track of like which kind of character did I just see based on which kind of state am I in, and how do I move around. So it's just a loop with a big nested if else. I hope you can see that. And then there's some extra work to do on this transition where you add to your count variable / register, right, if you're doing this in assembly. But that is an easy way to correctly count the number of words in any text, regardless of how many spaces the user likes to use. That's perfect, and this is exactly the algorithm that is deep inside of like Google Docs or Microsoft Word that's counting words for you, okay? This is the good one that does it right, okay? So think about how you'll implement that, because that will be your job later. All right, now we're ready for floating point numbers. All right, there's a nice website that helps with learning about them, float.exposed. So if you go to this website, there's a way to show, like type in whatever you want, like what's the floating point encoding of, I don't know, 2.75, I'm not sure. And then once you like click away, it is changed and it shows you as a float or as a double, whatever you want. Floats are only 32 bits, doubles are 64 bits. It'll show you all of the different pieces, and it will like highlight them, like underscore, here's the red parts, the green parts, the blue parts. They're different pieces. They're encoding different parts of the floating point number. And yeah, it's kind of trying to tell you what it means, okay, and how to interpret it. So it's a useful website to play around with as we learn more about it. But I have a question for you, all right? So let's see, how do I want to do this? I will eventually have a question for you, all right? So let's kind of talk about how floating point numbers work first, though. This is ones and zeros somehow having a decimal place in it. It's not obvious how this was done, okay? It's an encoding. It's not something that humans can usually just look at and understand, okay? So at least now we're going to learn how to make fractional numbers. It's going to take some work, but at least we'll finally know how it works deep down. The standard is called IEEE 754, all right? That is the encoding of floating point numbers that everybody has agreed on and every processor has decided to implement, okay? It's a binary format, so it's ones and zeros in some weird way that make your floating point number, okay? So that's that. And your floating point numbers could also be negative, of course. Boop. That changes something, doesn't it? And it takes 32 bits to store a float. That's your float type, right? That's called a single precision floating point number, and that's exactly why double is called double. It's 64 bits, double the size of a float. Okay, so yeah, let's first, right? It's floats and doubles are representations of decimal numbers in binary, essentially. So let's learn how to make fractional numbers in binary. All right, so here's a question for you. I'd like you to try this. All right, here is a binary number with a decimal place. This is a little odd. Okay, what should this be? All right, what should this be in decimal? Do you remember how to break this down? Like this side, this was 1 times 2 to the 0 plus 1 times 2 to the 1 plus 0 times 2 to the 2 plus 1 times 2 cubed. What happens on this side of the decimal place? Or better yet, what happens with a decimal number? How do you break it down into okay, that's the tens place, the sevens place. This is, for decimal numbers, is the tenths place, the hundredths place. Is there some fractions of exponents that are there some exponents that you could use to continue this idea? That's my hint for you. Try it in binary. Okay, how does that continue down on the line? All right, down after that decimal place. So first of all, this idea. How do you break down this decimal number? It's going to be, well, it's going to be plus 5, right? 5 times 10. This is the tenths place, right? This is the tenths place. So it's 10 to the negative 1, which is exactly what we wanted, right? That's the 0.5. 5 times, it's going to be 1/10, yeah? That equals 0.5. That's exactly what we want there. And then this next one, following that pattern, that's going to be 3 times 10 to the negative 2, which is the hundredths place, right? That's 3 times 1 over 100, which contributes that 0.03, which is exactly, again, what we needed here. So, following that pattern, this part, this is the whole number part, which we know and love, that's going to be what? Let's try to do it in order. This is 2 to the 0, 2 to the 0's place, plus 1 times 2 to the first, 2 to the first, plus 0 times 2 squared, so I won't include it, plus 1 times 2 cubed, so plus 2 cubed. All right, that's the whole number parts. Now let's do the fractional parts. This is plus 1 times 2 to the negative 1. 2 to the negative 1 plus 0 times 2 to the negative 2 plus 1, so I'll include that one, 1 times 2 to the negative 3. All right, that's what this number is representing. Does that make sense? So the whole number, at least, that's 8 plus 2 plus 1, so 11. It's 11 point something. What are these guys? All right, we have 1 over 2 plus 1 over 3, right? Because that's a negative 3. That's supposed to be a negative sign. I don't know why it looks a little weird. Let me fix that. There. Sorry. And then I did this completely wrong. It's 1 over 2 cubed. Excuse me, not 1/3. 1 over 2 cubed, 2 to the 3. And that's what 2 to the negative 3 is. So that's equal to 1/2 plus 1/8, which is, I don't really remember. I wrote it down, but I'm not going to force you to remember these things. It's, all right, what's 1/2 plus 1/8? 0.625, apparently. 0.625, and so this binary number with a decimal place is the number in decimal 11.625. I guess you can't call it a decimal place anymore, can you? It's like a binary place. But yeah, that is this number back in decimal. Okay, I don't know if that makes sense. So you can have fractions, that's totally fine. That is totally fine. All right, so now let's talk about the encoding. So now that you know how to do it, okay? So IEEE 754, the standard for implementing floating point numbers inside of a computer, it's going to split them, each number, into a sign bit, an exponent part, and a thing called a mantissa. All right, so this is going to store your numbers in essentially binary scientific notation. Okay, so we're going to talk right now about this. This is the encoding. We're going to talk about the encoding for floats, so 32-bit floating point stuff right now. 32-bit only, but this generalizes to 64-bit doubles as well. So we're talking right now. We'll focus on the float type, but everything we say will apply as well to double. Okay, so yeah, every number as represented as a 32-bit float will be split up into a sign bit. There's only 1 bit needed for that. There's an exponent part. We're going to dedicate 8 bits of our 32 for that, and all the rest goes to something called a mantissa. 23 bits for that. Okay, so what we're going to do is we're going to store our numbers not like this. It still will be kind of like this. We're going to store it in binary scientific notation. So that's like this, right? If you convert our one that we had before, it would translate this into, like, you got to move the decimal place over a few times and figure it out what that means, like 1.011101 binary still times 2 cubed. Okay, it's not 10 anymore, not times 10 to the something. It's binary scientific notation. All right, and so yeah, and then you have to like pick what goes in each of these places: the sign bit, the exponent, the mantissa. All right, so the first thing is the sign bit is an easy one. It's 1 if your floating point number is negative, and it's 0 if it's positive. So we're going to have 0. All right, for this example, it's going to be 0. Our sign bit 0 because we're trying to represent a positive number. Okay, so there's that. What else? The next part is the exponent. It's going to be 8 bits that represent the exponent in scientific notation. But because we would like to represent negative exponents as well as big positive ones too, we need a way to encode negative as well as positive exponents here. And so we're going to bias, or we say we're going to bias our exponent by 127. So what we're going to do is we're going to take our original exponent, whatever we're trying to store, so 3 is what we were really trying to store, and we're going to add 127 to it to make sure that even if it was negative, it will be a positive number as we store it. All right, so 127 is the bias that lets us like have a negative exponent. Cause like if it was 2 to the negative 3, now we're just going to set the exponent part to 124. Okay, that's kind of the idea. But for us, if our exponent is 3, our exponent bit here stored as 8 bits will be 130. We're just going to represent 130, and that will be our exponent part. 130 for this example. All right, and then the last part is the mantissa, and this is for the actual number itself. Okay, so that's like this part. So we've stored the sign, we've stored this exponent in a certain way. We just still need to store all these guys, and that's where the mantissa puts it. All right, so actually, if you think about it, every number in binary scientific notation, like you go until you see the first real digit, and the only thing that could be your first real digit in binary is a 1. All right, so every number in binary scientific notation, we know it starts with a 1, so we're just not going to even store that. We know it's there, so we'll just store these guys. So we're going to store only this part, the part after the dots. All right, all binary scientific notation numbers have to start with a 1, so we don't need to include it. We get 1 extra bit that way to save for our precision. All right, so this is going to go in there. All right, that's the idea. And so, yeah, that's just like, I hope that makes sense, right? No scientific notation number looks like this. You don't do it like that. Instead, you move it over. You go to the first real digit, 1.101 times. It's times 2 squared. Okay, that's the goal. All right, when we're trying to represent really the number 110.1 in binary. Okay, so yeah, that's what we do for the mantissa, and that's what that will look like. So let's put this in the website 11.625, and now it'll make sense. Clicking float, of course. So yeah, the sign is 0, so 0, and then 130 because we're biasing our times 3, right? Times 2 to the 3rd power by 127. So this is that encoding 8 bits that make up 130. And then the rest is everything after the decimal. So it was the 0, 1, 1, 1, 0, 3 ones, 0, 1, and the rest are zeros because we don't need that much precision. There's nothing after that. Okay, so that's why it works, and that's how we store it. And the computer somehow knows in the circuitry somewhere how to add those weird looking things. Okay, so yeah, let's do our example in depth. All right, so we had this guy, we know what it is, it's 11.625. Let's actually convert it to actual float stuff. So let's write down everything I said. All right, so this guy as a float. So first step is convert it to binary scientific notation. All right, so we've got to move over the decimal place. This is times, right? Right now it's times 2 to the 0. Then move it over 1, 2, 3. That's where we need to put it. So this needs to be, it's this times 1 point all that times 2 cubed, so that we move it right back to where it needs to go. Okay, so that's your binary scientific notation. And we figure out the sign bit. It's going to be 0 because it's a positive number. All right. And then the exponent is 3, and we bias it by 127. So the exponent as an 8-bit number needs to be 130. 130 as an 8-bit number, so it's that part. And then finally, we do the mantissa. The mantissa is everything after the decimal because we know it needs to start with a 1 anyway. We're not going to save that. So we chop off the 1. We don't need it. We know it's there. And then we store that as a 23-bit number to start it off. And like, if we needed more, if we had more decimal places, we would include those, but we only have this many. The rest become zeros, all right? And then you put it all together, and that is how you represent as a 32-bit number our 11.625, okay? So that's how it's going to be stored. I hope that makes sense. All right, your turn. So please manually, don't cheat. Make negative 12.5 as a float, all right? Single precision float number. See if you can do it. Remember that you're going to have to bias by 127 for the exponent, all right? So I'll go here so you can pause it for a second, but you try now, all right? Negative 12.5. All right, if you think about it long enough, what's we got to make positive 12, right? What's regular 12.5? It's going to be 8 plus 4, right? So that's 12 in binary, negative that, and then 0.5 is going to be 0.1, isn't it, in binary? Because this is 2 to the negative 1, which is 1/2, which is 0.5. Perfect. So yeah, remember that 1/2 is 2 to the negative 1. That's the 2 to the negative 1's place after the not the decimal point, I guess, after the binary point. All right, so that's the first step. Then we transform this to binary scientific notation. So we gotta like move it over a few times. It's gotta be negative 1.1001. That's right, yeah. Now we gotta move it over 1, 2, 3. All right, so times 2 cubed. That's binary scientific notation. And then, all right, what do we got? The sign bit, it is a negative number, so it'll be set to 1. So S will be set to 1. And the exponent, again, it's times 2 cubed, so the exponent is 127 plus 3. So it's again 130. And then the mantissa is everything after this 1 here. So it's going to be 1001. And then a bunch of zeros to fill in the 23 bits that you get for that. All right, so just if you convert that to binary, that's going to be your answer. Okay, so that is hopefully helping you. And yeah, there are a couple special cases of floating point numbers. If you go and read the standard if you want to know more about this kind of stuff. But we are going to set aside 0 and 255, so all zeros for the E and all ones for the E. We're going to interpret them specially, all right? So that means it's impossible to have an exponent of a negative 127 or 128. We're throwing away some very small numbers as well as some very large numbers for this, okay? So what we're going to do is, here's what it means. So if E is 0, all right, so it's all zeros, then it depends on the mantissa, what we're trying to encode. So if the mantissa is also all zeros, all zeros, exponent all zeros mantissa, then it's either, then it's representing the number 0. All right, so it's either representing positive 0. There's also such a thing as negative 0 if the sign bit is a 1 in IEEE 754 floating point land for weird reasons. Okay, so you can have either positive or negative 0, and that's how you encode it. Okay, that's how 0 is encoded. If the exponent bits are all 0, but the mantissa is not 0, then it represents what's called a denormal number, which is supposed to be representing a very small number. All right, so we're going to have that encode some number that starts with a 0, actually, 0 point mantissa times 2 to the negative 126. All right, and it can still be positive or negative based on the sign bit. So it's going to let you represent very small numbers this way, super duper small. That's the smallest they could get, all right, with this sort of exponent. All right, so that's that. That's when E is 0. If E was all ones, if E was set to 255, then, again, it depends on the mantissa. If the mantissa is set to all zeros, then it's either positive or negative infinity based on the sign bit. So that's how you represent infinity. Infinity is encoded especially as a float. All right, so that's infinity. And if E is all ones, but the mantissa is not all zeros, it's something other than all zeros, then it represents nan, which is short for not a number. All right, so that's some number that was unrepresentable, that the math just didn't check out on. So for example, if you divide by 0 with floats, you get back nan. So that's just an unrepresentable number. Okay, that's how that works. The sign bit can be anything, the mantissa can be anything, as long as it's not 0, and the e is stuck at all ones to represent not a number. All right, so you have a bunch of different options for not a number. Okay, though if the first bit of m, if the very first bit of that mantissa was a 0, then we call it a signaling not a number, signaling nan, which is going to throw a floating point exception in your code. It'll end up being a runtime error, in theory. Otherwise, it's called a quiet nan. Okay, a quiet nan doesn't complain. All right. So yeah, there's two kinds of nans. One that's supposed to mean problem, or one that you expected to happen, and so it's just not going to alert anyone. Okay. So those are the special cases of floating point land, and we were talking about 32-bit things right now. This image, we're talking about floats, the float type right now. Everything else, like all this stuff that we're talking about, works for doubles too. All right. So here's what doubles look like. They still have a sign bit. They use 11 bits now for the. This is the picture of how doubles work. They use 11 bits for the exponent, and they bias by 1023. So you can represent some much larger exponents, and also some much smaller exponents as well with your doubles. And then the mantissa part, you get 52 bits, so you have extra precision, right? So that's quite nice. And so that's doubles. There's also something called half precision, which is not really a type you can make very easily in C++, but like a lot of artificial intelligence likes to use this because it's just small numbers, and so like they have still a sign bit. You still need one of those for sure, and then the exponent is tiny. The fraction part is tiny, the mantissa. And then there's also a thing such as quadruple precision. So that's how many bits is that? 64 doubled, right? 128 bits to represent a fractional number with quadruple precision. That takes a 15-bit exponent biased by this giant number, and 112 bits for the mantissa. So that's crazy. Extra space. Okay? So yeah, you can use, this is how doubles look. It's pretty much everything we've been talking about is true for doubles. It's just like you have to bias by something different, and you have more space for your mantissa. All right? So yeah, let's talk about now just a sneak peek of floating point assembly. All right, floating point assembly is possible. It's happening in the floating point unit, the FPU on your machine. So it's a special, different place, and it has its own registers too. So let's talk about that. So though, right, we have X registers, and those are 64 bits wide. You could technically shove a double in an X register. All the floating point stuff is still happening in the FPU because it's what knows how to like add floating point numbers, like put it back in this weird encoding. Okay, so the floating point unit has its own registers. They're called D0 through D31. You get 32 spaces, 32 registers for doubles, and then there's also, just like you had your X registers and your W registers, you also have S0 through S31 for singles floats. Those are just your single floating point numbers. And they're like they're the right half of the D registers, exactly like W and X registers play along together. So there's that. So here's a silly example of some floating point assembly. Let's calculate pi. All right. There's a CMath library function called atan, which does inverse tangent. If you take the inverse tangent of 1.0 and you multiply it by 4, that is pi. Okay, because this inverse tangent of 1 is pi over 4. So let's calculate pi together. Here's the relevant code. You can do a move into a D register. You just say F move. A lot of these things start with F's now because we're doing floating point stuff. So floating point move into a D0 register in the floating point unit, 1.0. Okay, and that's actually where your arguments go. Just like X0 is your first register when you're calling stuff for normal assembly, when you're doing floating point function calls, D0 is like that equivalent of your first double argument. And then you can BL ATAM, and then the answer is getting returned to you as a double in D0 again, just like X0 holds the normal whole number answers. So that's kind of how that works. And yeah, this is fmove again. There's the 4.0 into another D register, and it's fmul to multiply them back. And so like your answer's in D0. And yeah, if you want to print a double, you have to use a special float, like it's %LF or something. It's like %F or something like that. Well, I have it in my notes. I'll show you in a second. And then because you want to print a double, you give that as an argument to printf in one of the double registers, so in D0. And it's already there. So let me just code this up, and it'll make more sense as I do it. But that's pretty cool that you have those options now. Call this pi.s, and I will steal all that file. There we go. So I do not need any x19s. Boop. And I do want to return 0, so that's good. So yeah, let's do all these. Let me print them out and heavily comment them. All right, so let's move 1.0 into the D0 register as a double. All right, so it's going to be fmove into D0 number 1.0, perfect. And then we want to call atan on 1.0. And the atan function just takes a double, gives you back a double. When you're doing floating point assembly, the first argument goes in D0. So we can just BL atan, it'll figure it out, and we'll get the result back in D0. It's like D0 is the double equivalent of your x0 for everything else, right? So D0 holds right now pi over 4, given what atan does for us. And so we want to multiply it by 4. So let's move 4 into some other D register, so D1. So fmove D1 4, and then let's multiply. Multiply D0 by D1. And store the answer back in D0, so it's fmul. D0 and D1, back into D0. And so now D0 itself holds pi. Okay, that's the answer. And we'd like to print out pi. All right, so we want to BL printf to print out our pi. And the way that you print a floating point number to printf, the format string will look like this. It's going to be %f. That's how you pass along, and you say expect to see in your next parameter, in your argument to printf, expect to see a floating point number as a double. So go looking for a double argument as well. So let's get our, let's see. The format string for printf still goes in x0. The format string is the first argument for printf. So it goes in x0 as usual. And then, if you have your second argument, and it's a double, it doesn't go in x1 or anything, it's going to stay in one of the D registers, your first double argument goes in D0. And then printf expects the double arg in D0, and it's already there. That's where we put it ahead of time, okay? And it's already there. Beautiful. So that should do it. Interesting, huh? So that's the relevant code. So GCC, the way you compile this is a little special. We have to say, by default, it doesn't do this. We have to say, please GCC link the math library so that we have access to it. Link the math library. Okay, that's what -lm means. GCC pi.s-o pi as -lm. And then we can /pi, and what do you know? There it is. Beautiful. All right. So yeah, that is what I wanted to talk about today. That's some information on how to mess with strings, as well as a taste of floating point. You at least know how all floating point numbers are encoded now. And so think of all the hard work that your CPU has to do to mess with those guys. So yeah, that's where we'll stop for the day.